Good morning, my name is Adam Eldridge. I'm a West Valley High School math teacher in Yakima, Washington, also part of the Cornerstone program through Central Washington University. And today we're going to introduce trigonometry to you. So we'll be looking at out of the Centrals book, section 6.1 today. So to start with, I want to talk about our objectives and what you're going to learn about today. We're going to talk briefly about degrees, minutes, and seconds. We're going to talk about the 6 trig functions in a right triangle, calculating exact values and approximate values of a right triangle using trig, and calculating exact values, got a typo there, of trig functions in special right triangles. So to start with today, let's talk a little bit about some things to remember about angles. Back in geometry, you learned that an angle is 2 rays that meet at a common endpoint. So, we have the right tool here. We've got 2 rays that meet at a common endpoint. Again, the name of that common endpoint is a vertex, so vertex, that point right there. We classify angles oftentimes as acute, obtuse, or right. Acute angles are those that are between 0 and 90 degrees. Right angles are those that are 90 degrees. And for today's lesson, we'll focus on obtuse being between 0 and 180. Now, down the road, we're going to be looking at angles where it's important to know whether we're measuring it clockwise or counterclockwise, and we'll talk about angles that go beyond the scope of 0 to 180. But that's for discussions down the road, as we will primarily be working with acute angles in right triangles today. The next item here is decimal degrees versus degrees, minutes, and seconds. If you've ever done much in the world of navigation, you'll have seen angles reported in such a fashion as this, where you'll see 27 degrees, 14 minutes, and 30 seconds. So again, if you look at maps, you'll often see lines of latitude and longitude listed this way. Depending upon your GPS device, you may see it listed this way. Most of the time in mathematics, we prefer to work with it in decimal degrees. So let's take a moment and convert a number like this into decimal degrees. A degree first of all is 1/360th of a full rotation. Minutes, there are 60 minutes in a degree, much like there are 60 minutes in an hour, and there are 60 seconds in a minute. So if we want to convert everything into decimal degrees, our degrees here is 27. And then we are going to add to that 14/60ths. Because again, there are 60 minutes in a degree. And we are going to add 33,600ths. Because there are 60 minutes, or 60 seconds in a minute, and 60 minutes in a degree, so 60 times 60 is where we get 3,600. So if we pop over to the calculator here, we can convert by taking our 27, adding our 14/60ths, and adding our 3,600ths. And we end up with 27.242 rounded to the nearest thousands. Again, we don't see this notation too much anymore. It was more used back before we had a lot of the graphing calculators and scientific calculators that we have today, but something you may encounter in your textbook and on exams. So moving on here, let's introduce the 6 basic trig functions. Back in geometry, you should have been exposed to these first 3 right here, sine, cosine, and tangent. Now, down here we've got a right triangle. Let me label angle C as our right angle. And all of the trig relations are relative to the triangle that's being drawn here. So in our right triangle, I have angle C as my right angle, and angle theta here is at the vertex A, and that's what we're going to be looking at each of these ratios. So relative to angle A, or in this case I'm calling it theta, The side opposite would be the one that is not making up the angle itself. Our hypotenuse is always the side that is opposite the right angle, and the adjacent is the other ray, or in this case it's a segment part of that ray that makes up angle theta or angle A. So we define the trig function sine as being the relationship or the ratio between the opposite side of the angle and the hypotenuse. Cosine would be the adjacent over the hypotenuse, and tangent is the opposite over adjacent. Now again, most of you in the room would have taken geometry and algebra 2 trig where you've seen this before. Most of my students will think of this as SOHCAHTOA. Little acronym to help you remember which ones are which. Sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. In pre-calc, we kind of expand on our trig functions to include these other three functions over here: the cosecant, the secant, and the cotangent. Cosecant of theta is defined as the hypotenuse over the opposite, which you'll notice is 1 over the sine of theta. Secant is hypotenuse over adjacent, which is 1 over the cosine of theta. And cotangent is 1 over tangent. We'll discuss this more in lesson 6.2, where we'll be looking at some of the different trig identities. Now typically when we're dealing with right triangles, we are going to primarily work with the SOHCAHTOA, sine, cosine, and tangent. But in calculus, there's some nice identities we'll be looking at down the road in trig that will allow us to do some substitutions where we can manipulate seemingly ugly equations into ones that are a little less cumbersome by substituting things like cosecants, secants, and cotangents. So at this point, I would probably pause the video. If there are any questions, your instructor can supplement any of the trig relations at this point. And we're going to move on and look a little bit at reminding you what a trig function is. And my students have always struggled with what a trig function does versus the inverse trig function. And throughout your pre-calculus experience, you've talked a lot about the concept of a function being an input mapping to an output. It's important to remember that with trigonometric functions, sine, cosine, tangent, that the input is an angle. We are taking the sine of an angle, and the output is a ratio of sides. Hugely important, because when we add in the inverse trig functions, we're going to look at inputting a ratio and working back to an angle that corresponds with that ratio. So today, we're going to look at taking angles and using that angle to calculate ratios related to side lengths. For a given acute angle, the values of the trigonometric functions depend on the ratio sides, but not on the size of the particular right triangle in which it resides. For example, if I were to take two triangles, and in this triangle I had 5, 12, and 13, which is one of our common Pythagorean triples. Actually, I should work backwards here. Let's go 50, 130, and 120 there. And if I were to compare that to a 5, 12, 13, this angle here and this angle here, they are the same. And the ratio that corresponds to each of these angles will be the same in both triangles. For example, if we call this angle A, sine of A is equal to 120, that's the side opposite, divided by the hypotenuse, which is 130, and I'm running out of room there, which reduces down to 12/13. Looking over here, again, we'll call this A prime. Sine of A prime is also 12/13. For this angle, it doesn't matter if we're talking about this triangle or this one. The angle measures the same because the triangles are in fact similar. So when we are using trig functions, like the sine function, we are getting a ratio of sides. Sine specifically is relating the side opposite that angle in the right triangle to the hypotenuse. So just as a big idea, remember that trig functions are giving us a relationship between an angle measure and a ratio of sides that correspond. So in this figure here, where C is also my right angle, I want you to take a moment and determine the 6 trigonometric functions of an angle for this particular triangle. Now, I gotta get that. There we go. So it's not showing up very big. This side length is 3, this side is 4. First idea here is we have a right triangle where we know the 2 legs, but we don't know the hypotenuse. So you ask yourself, how do I find the hypotenuse of a right triangle given 2 legs? Immediately you should go to the Pythagorean theorem. So we can find the length of AB by using the Pythagorean theorem. 3 squared plus 4 squared, so AB squared is equal to 9 plus 16. AB squared is equal to 25, and AB is equal to plus or minus 5 when we take the square root. We're going to deal with the positive root 5 at this point. So take a few moments. Again, this would be a time to pause and give me the sine of A, the cosine of A, the tangent of A, cosecant of A, secant of A, and cotangent of A. So hopefully you've had a moment to do that. Here is our angle A. Our sine is 4/5. Cosine is 3/5. Tangent, 4/3. So opposite over adjacent. Again, this is all relative to angle A. Our cosecant is the same as 1 over the sine. So 5/4. Secant is 5/3. And cotangent would be 3/4. Again, today we're focusing on right triangles and we're dealing with acute angles. A and B here are acute. When we start working in the coordinate plane and on the unit circle, you'll see angles that don't fall between 0 and 90, and we may want to take a slightly different approach at that point. Now, one of the other objectives today was to look at how we can calculate sine and cosine values on the calculator. We want to find approximate values of angles. So, if we want to find the sine of 40 degrees, I can almost guarantee that right now, if you open up your calculator, and this is the first day you've been working with trig, and you've got a TI-83, TI-84, TI-89, if you go sine of 40 degrees, you're going to get different answers across the room. Because I can almost guarantee that some of you will be in degree mode, and some of you will be in radian mode. And this is one of those times where it's crucial that we know what mode we're in, so we eliminate the errors associated with that. So let's head over to our TI calculator, and on our TI, 83 or 84, we can start by hitting the sine of 40 degrees, closing our parentheses, although that's not completely necessary with the TI. Before I hit enter, I want to check my mode, and I have already put my calculator over in degree mode. If you're not in degree mode, you could change to degree mode by hitting your down arrow and then over the right arrow so that it's blinking on top of degree, and hitting enter will make sure that it is in degree mode. So that is how we can get to degrees. And And we want to quit to get off of that screen, come back and hit enter. And that means that the ratio of sides in a right triangle, where the opposite side of a 40-degree angle relative to the hypotenuse is 64/100ths approximately. Similarly, cosine of 40 and tangent of 40. And just to see that we didn't need to close our parentheses there on the TI. But it's just a good habit to always close parentheses as much as possible. So these numbers here, the 64/100ths, the 77/100ths, and the 84/100ths, those represent ratios. It's key to remember that our input was an angle and the output is a ratio of sides that correspond. Now, the other three trig functions that we talked about, the cosecant, the secant, and the tangent, you'll notice that the calculator doesn't have buttons for these. And I want to caution you, because the next big mistake that students will make is on our TI screen here, the inverse function of sine. Right above the sine, you'll see a sign to the negative first. That does not mean the reciprocal of sine. It actually means the inverse sine function, which we're going to talk about later down the road on another day. So what we want is we want the reciprocal of sine, and we are going to implement this button here. So if I want to find the cosecant of 40 degrees, cosecant is the same as 1 over sine. So I've got a couple ways I can do that. I can start by taking 1 divided by the sine of 40, using my parentheses. Or I can take the sine of 40 degrees and then take its reciprocal, 1 over that value. And you'll notice I end up with approximately 1 56/100ths. Similarly, we would find secant by taking 1 over the cosine, and we could find cotangent by taking 1 over the tangent function. So let's head back to our main lesson here. So we've hit on the first couple here. You've got using. It's important that we are in degree mode if we're dealing with degrees. Later on in chapter 7, section 1, we'll look at radian mode. Don't use the inverse trig keys. Use the reciprocal button. Take it 1 over, or use to the negative first power. Using function shorthand that the calculator doesn't recognize. I'll tell you, if you're using a TI-30 or a non-graphing calculator, on those calculators, you oftentimes will enter the angle measure first. So if you wanted to take the sine of 40 degrees on my old TI-30, you would hit 40 and then hit the sine button after you typed in the 40. Be careful with your parentheses, because sometimes when we start having multiple arguments inside of those parentheses, we need to close those parentheses before performing an operation. So that's kind of the nuts and bolts on how to use a calculator to find a trig function value. Our last big idea today is to review a couple of special right triangles from your geometry days. And the first one we're going to look at is a 30, 60, 90 triangle. And I've started by putting an equilateral triangle on this screen here. So we have 60 degrees, 60 degrees, and 60 degrees. And one thing you'll remember about equilateral triangles, they're equiangular as well. And I'm going to call each of these side lengths 2x. There's a specific reason why I want to do that. But we know that all these sides are the same. X could be any number, because again, we're talking about all equilateral triangles are similar. Take you back to your geometry days. And so the sides are in proportion. All of the side lengths in an equilateral triangle are equal. Now, if we take this equilateral triangle and we cut it in half through the vertex perpendicular to the side opposite that value, what we create here is another triangle that I will write out over here, where this angle has been bisected is 30 degrees, this is still 60, and we drew our altitude, which is also the median, which is also the perpendicular bisector, because we have an equilateral triangle. And we have a 30, 60, 90 right triangle. This side here is one of the sides of our original triangle, and it is 2x. From geometry, you'll remember that this median, altitude, perpendicular bisector means that I have a line of symmetry here. And I could fold this vertex over onto this one in relationship to this line here that cuts that triangle. So that cuts that bottom side into half. So if the long side is 2x, then my short side is x. And then if I use the Pythagorean theorem, I can find the length of this side. Let's call it a for now. So 2x squared quantity is equal to a squared plus x squared. So that side we're looking for is squared is equal to quantity 4x squared minus x squared. So I squared the 2x and subtracted x squared from both sides. I've got a squared. I want to know what a is, so I'm going to take plus or minus the square root. Again, I'm going to only deal with the positive in this particular example today, and I'm going to end up with square root of 3 times x. And I usually like to write that as x times the square root of 3, just because with my handwriting, sometimes it's unclear whether or not the x is underneath the square root, so I'll write that out front. Again, different books will do that in different ways. This is the ratio of sides of any 30, 60, 90 triangle. And since it doesn't matter what x is, for memory purposes, we can just say that the short side is half of the longest side, and our middle side, opposite the 60-degree angle, is square root of 3 times bigger than the smallest side. Now, why would we do this? Well, if we want to look at trig values, exact values of certain angles, we can use these ratios to calculate the sine of 60 degrees, for instance. So, if I were to take the sine of 60 degrees, I can draw a 30, 60, 90 triangle, like we have right here. And I know that if this is my 60-degree angle, the side opposite is root 3. Relative to this side, the hypotenuse being 2. And if you were to check that on your calculator and take the sine of 60 degrees, you would see that it's the same value as if you took the square root of 3 and divided it by 2. Our cosine of 60 off of this triangle would be the adjacent side, which is 1, divided by 2, which is 1/2. This will become extra important when we get back on the unit circle and start talking about angles like sine of 300 degrees, sine of negative 120. We're going to want to be able to draw our 30, 60, 90 triangles. A lot of my students think that square root of 3 is the largest side because they think that the 3 is bigger than the 2. Well, 3 is bigger than 2, but the square root of 3 is smaller than the square root of 4, and 2 is equal to the square root of 4, so the largest side is the 2, the middle side opposite the 60 is root 3, and the smallest side is 1. That ratio is true of every 30, 60, 90 triangle. And the way that I remember it is I go back to my equilateral and go from there. So one of my big ideas is to always try to memorize less and understand more. I know a lot about equilateral triangles from my days in geometry. If I'm trying to memorize everything, I'm going to sometimes confuse which sides are which. But if I can take it back to something I know and visualize what's going on here and why it works, I have a better chance of remembering that down the road. We've got one other special right triangle I want to talk about. And this one is a 45, 45, 90 right triangle, which again, I want to take you back to your days of geometry, connect this to something that you've done previously. And again, some of you in the room may be sitting there going, I memorized these a long time ago, and great, you can fast forward through this. But inevitably, when I have students take a test for me, they kind of get a little bit more anxious than they are when they're doing their homework, and they freak out a little bit if they can't remember, is it 1, is it square root of 3, is it square root of 2? I don't understand which one it is. I always like to take it back to a picture. If these two angles are the same, then we know that these two sides are the same. It's an isosceles triangle. Base angles of an isosceles triangle are congruent. These are congruent sides in our isosceles triangle. So let's call each of these sides x, And again, break out the Pythagorean theorem because we're dealing with right triangles today. X squared plus x squared, I'll call this one c this time, is equal to c squared. So 2x squared is equal to c squared. So c is equal to plus or minus the square root of that thing. We're going to look at square root of 2 times x, which again I typically write as x roots of 2. X can be any value we would like it to be. We just know that the hypotenuse is square root of 2 times bigger than whatever the side lengths are in our isosceles right triangle. So if I want to find the sine of 45 degrees, sine of 45 is x divided by x roots of 2. Those x values, provided it's not 0, will cancel out. We're left with 1 over root 2, which we don't always like it in that form. We can rationalize our denominator by multiplying by 1, a very special one that is square root of 2 divided by square root of 2, and we end up with square root of 2 over 2. So just as a quick note here, simplified ratio of a 45, 45, 90 is our two legs are the same and the square root of 2 times larger, the hypotenuse is square root of 2 times larger than either of our two legs. So for our last concept today, take a moment here and find the values of all 6 trig functions for an angle of 45 degrees and for an angle of 60. Pause it if you'd like, but I'll go ahead and write those out here. So sine of 45. Yeah, I'm going to draw myself a picture just to help me remember. It's going to be root 2 over 2. Similarly, cosine of 45 degrees is root 2 over 2. If you haven't noticed yet, in this triangle here, if this is the angle A, sine of this angle has a relationship to the cosine of this angle that we're going to get back into a little bit later. And so we'll talk about that in an upcoming section. I'm hoping some of you have already been able to make that connection between sine and cosine values in our triangle. Tangent of 45 is going to be 1 over 1, which is 1. And then I like to write their partners that go with them. So sine goes with cosecant. So cosecant of 45. So cosecant of 45 would be hypotenuse over opposite. Root 2. Secant of 45. 1 over the cosine, which is also root 2. And cotangent of 45 degrees is 1. For our 60-degree angle, we did sine and cosine earlier. Quick triangle here. Living out of room. This is my 60-degree angle, right angle, root 3 and 2. So sine is root 3 over 2, cosine is 1/2. Tangent of 60 is root 3. And then the reciprocal relationships here, cosecant of 60 would be 2 divided by the square root of 3, which is 2 roots of 3 over 3. Secant of 60 is 2 over 1, which is 2. And cotangent is root 3, 1 divided by root 3, which is root 3 over 3.